So hi everybody, my name is Kamel Belhous. I'm based in Boston. I work for Teradyne. And today I'm going to talk about a very exciting topic. It's an original new ID. It's going to be about a defect table in Systemverilog. Sounds fun, huh? So can you guys see my slides again? Can everybody see my slides?
We can see them, yeah. You're not in presenting mode, is the only thing. Yeah.
Okay. So, yeah. So this was developed by a team at Teradyne and our friends from CorrectDesigns in Austin, Texas. And so this is about the lean technique. Lean means, how to minimize waste, how to minimize waiting time. We're going to start with an overview and then show some model examples. We're going to show how is the table built, and then talk about audits, and then talk about enhancements. So how do we keep the verification environment stable? I mean, how do we prevent the failures in the regression for the features that used to work before, right? How do we maintain a high pass rate for the regression? And how do we release a chip knowing that all the workarounds all of them have been removed, all the fixed needs and to-dos? We want to do all of that while the RTL and the checkers and the tests, they are being added and debugged. So this presentation is about an executable defect table. Executable because it is in Systemverilog, it compiles, it runs in the simulator. This is used to track and work around the issues for the design environment and also for the test bench, to go around test bench issues. The existing regression suites can continue to be used to qualify changes and find new unknown flaws in the code base. What does this mean? I'm sure we've all been in a place where we had a regression running, the pass rate was pretty low, we had a lot of tests failing, and guess what? That stops us from, or slows us down from finding bugs. So sometimes you wish the regression rate was like 100%, but it's, it's not always possible. But with this technique, you can do that. So the verification engineers can make progress, again, without being slowed down by the bugs, which haven't been fixed yet by the designers. It's a lean technique. It's used to reduce the waste, waiting, delays, by providing the ability to mitigate the productivity losses caused by the delays introduced by design spec and verification changes for the bug fixes. Defect table. There are a lot of words on this slide. You may not get everything. It's going to be easier when you look at the code. Engineers love code, but I think, I try to simplify it a little bit. So basically, the defect table, you can see that almost as a copy of your defect tracking system. There are many, many defect tracking systems on the market. Some of the most well-known are like Jira, Bugzilla, ClearQuest, and others. So you can see this almost as copying, the bug ID from your bug tracking database into your Systemverilog code. And then you can take some actions around each bug. You create some workaround in the test bench. So you have each entry, each bug tracks the state of an issue of a bug. Each entry tracks the state of one bug. The defect state in the SV code can affect the behavior of the test bench. You can have checkers, workaround. So the table provides a disciplined approach. It has a clear SV class to keep track of all the workarounds in the test bench for the bugs which exist in the design or also the bugs in the test bench. It's a consistent, standard, way of doing things with the de facto locations where all the fixes will be in one place. The fixes that will affect the test bench behavior to provide runtime decisions on where you want to apply workaround or not. So it's a good model for DV engineers, but for designers too. And then it's also a way to review all the workarounds. The benefit is bigger and better the more bugs you have, or the longer time it takes for your bugs to be solved. And you can continue to add coverage. You can continue to have your tests running further and find other bugs and explore other pieces of the state space that wouldn't be possible if your test was just failing. The defect table is not a replacement of the bug tracking system. the bug tracking systems are pretty good. They're here to stay. They do their jobs quite well. What we're doing, we're just creating an image of that in the test bench to be able to take action around these bugs and make progress. Several ways of using the table. Some examples, you can demote scoreboards from errors to warnings. You can disable checks. You can change your constraints. For example, here, an example is that a register should not be set. The ADC should be set to busy only when the defect is closed. So you run your test, you have a bug, your test fails, it stops you from finding bugs. So you put like a workaround here, right? You put your busy, only when the defect is not in the closed state. So you put the ADC busy as a workaround so that your checkers do something different. And then the test doesn't fail. And then that allows the test to go further and find other bugs. So when you close, then once you have a fix from the designer, a few days later, a few hours, a few weeks later, then you set the ADC busy, you change its value, and then you have a fix, and then you can close the ticket. So then you set the ADC to 0, and then you can close your ticket. The scoreboard, you can do that. You can change the scoreboards via the UVM config DB. For example, you demoed them here to warnings, so your test can go further. And then, when you get the bug fixed, it passes, and you can put it back to errors in the config DB. So if something else bad happens in the future, it's going to still show an error. The constraints. So you have some constraints initially. So, and then again, you have a failure. So you go and change the constraints. You put them to original timing, and that's a workaround. Your test passes. Your test that still does something smart. You can still find bugs. And later on, once the designer comes in and he fixes his bug, you run the test. You change the constraint to minimum timing, and you can close the ticket. So these are just examples of actions, smart actions you can take around the bug. So smart actions don't mean if you have a data checker, for example, you can have different levels of granularity of your checking in your test bench, right? Some people may have a data comparator that they use for every check in the test in the DV environment. So we're not talking about putting a workaround about that type of checks, central checks. We're talking about other smart actions, about other distributed things you can do in the test bench without affecting your main checkers and your test execution. This is an example of the simulation output. So here, for example, you can see in the output file, you can see the list of the track defects. So you can see, for example, in our convention, we have, JASIC means RTL bugs. These are bugs from the database. You can see we have these 4 bugs, right? They are present, but guess what? They're not making the test fail. So your regression is still clean, and you can still have your test go further and find other bugs. You can still collect coverage and do all the good things you used to do. But we have also that for the test bench too. So the ones at the top, the DV issues, which, like pset, memory, modeling, LDLS reg, relay timer, these are test bench issues. Again, we do some workaround for the test bench to be able to progress further. But at least all the workarounds are listed here in one place. You can see them in the log file. And you can get different levels of verbosity of the workaround. This is just an example here, workarounds being applied to the list with the UVM info. So now the fun part, really, all of this was a little bit abstract. I'm sorry for that, but this is the real thing here. How is it really built? How do we do this? We have some common base source code for defect table. It's project independent. It's a base class that you can check somewhere central in your database. And then you do an extension of that class. And then, you populate it with your own. You do some overrides on the method and put your own information. So the base class has APIs for defining and accessing the defect. So your project just does an extension of the base class, and then you create the defects in there. And you can add your user code to query the state of the defect so that you can take different actions based on the state of the ticket. If a ticket is open, do this. If a ticket is closed, do that. And so it's really in one place. It's quite clean and cool because it's all in single place. This is the class, the base class. So the type def, you have to adapt it to your own, your own conventions for your bugs. In our case, it was just new, open, resolved, closed. We had many more, but we just simplified it here. And then you can see it's just an extension of UVM component. And then you can create defects. This is about creating every single defect. So every single defect, you're going to do that. Call the function create defect. And then you can change the state of the defect. And then you can add the features about adding details and actions on the defect. So this is the class, right? So you see the function, the build phase, just a standard UVM component, and then the create defect for every single defect, the state and the features and the description, and then the define defects. So define defects is the list, so that's where you put all your defects. You're going to see in the next slide. And then, some functions to access the state and change the state. You see, that's chip defect settings, for example. So you have the build phase again, and then in the define defects, you have all your defects in there. And then the suggestion is to have, different owners, organize the table by owners, so you don't have two people going and changing the same defect at the same time. And then it's a good location to take action based on the defect state. That's the adjust DV for defect. Like I said before, the three entries, PSET, memory modeling, LVLS, relay timer, these are test bench bugs, issues that you want to go walk around. These are not part of your official tracking system. Typically in the tracking system, it depends. Some people like to track their test bench bugs in their tracking system, which is fine, no problem. You can still do the same thing here. So constructing the defect table, is really, it's just a UVM component. You call it, it's in the build phase. You can have as many defect tables as you want and organize it in any way you like. Maybe one per block, one per IP, one per chip. You can just, put them in your environment. So when you're ready for tape-out, you can have automated reports about, looking at all your defects. And you can see here, you can see how many are open, how many are closed. You can see that from your test bench code. And it's nice, it's very nice, because, sometimes different people have different ways of doing fixes in the test bench. Some people use fixed needs, to-dos, so many different ways of doing this. And this is kind of a unified way of doing this. It's standardized, it's put in one location. I'm not sure if you've ever been in a case where you just commented a checker and you tape out an ASIC. These things can happen. So this kind of methodology will help you minimize that risk. And if you apply it properly, it will prevent that from happening. So I went a little bit fast, but the regressions, they fail only when you have new bugs. So your tests are really kept active. And the DV engineers are, not slowed down, not that much by the existing bugs, which haven't been fixed yet. That's super, super important. It's very dependent from product and company, right? We all got different type of bugs. We have showstoppers. We have typically some which are major or important, and some which are minor, less important. Some we don't care. So I'm not talking about the showstopper bugs here, because showstopper bugs, normally they should get attention anywhere, right? They block a lot of people, and typically they're resolved quite quickly. But you probably have a long list of bugs on any chip where you work, which are important. And as a verification guy, you want this to be fixed ASAP, and you want to keep finding the bugs, finding the next bugs until you finish the project. So the time, when these bugs are fixed, the faster it is, the better for you. And the slower it is, the worse it is for us. So this helps you when the duration to fix the bug is slow and the bugs pile up. So the log file can show you which defects affect the environment. And the automation easily indicates when an entry should be closed. You can see what's open and when you can close it. Or you can see on your to-do list. It's also good for designers. They can also use that. I mean, they can go, put the change in there and just, we have designers use the defect table too. So they're self-sufficient. They come in, they do the change, the constraint or whatever, and then they make the update. So again, very important is it provides the ability to thoroughly review the complete list of workarounds and to-dos. They're supported in a common manner to ensure the proper workarounds have been applied and removed before tape-out. So you don't need to worry about the commented code and whatever hacks are spread all over the place. You have everything in one place. I'm also a hacker too. So future enhancements. Really, this is the last slide. So we could add the command line defect override. Well, that's quite standard. So there, we can add that. That's the next thing. We can verify the fixes without modifying the code. And then you can enable rerunning the tests for reproducing the failures or testing the new RTL without code modification. The beautiful thing would be a system call to a live defect query where you could, from your Systemverilog code with API, you can then access the APIs of your real defect table. So you could compare, what you have in your test bench compared to what you have in your database. You could automatically run tests with fixed issues to check correctness. Imagine you go to use SV code, you had a bug before, the designer changes it, he changes the defect table action, and then with the API, they automatically go to your real defect database and update the ticket there. So that would be a cool thing to do, full automation. And this was a lean technique. This was about, we've been suffering a lot because of this, having a lot of bugs, taking a long time to resolve. The regression is in a really bad rate. Verification is always at the end, right? So whatever delay or whatever things happen, they're going to come to you as a verification, and the tape out date never moves, right? And on top of that, you get this type of issue where you get a lot of bugs that are not being fixed, and you can escalate, but people have different priorities and all that stuff. So this helps you by maintaining a healthy regression, and this helps you find other bugs. Without this technique, we would have found bugs much later, and our delays would have taken our project would have taken much longer to complete. So it's a very, 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 very powerful concept, and a very, very smart concept to help you make progress. And this comes from the idea of agile, of how to minimize waste and delays, where you sit down on a project, you see where are the bottlenecks, where are the issues, where are the wait times, and you try to minimize or ideally reduce that to zero, but that's not possible. So in the paper, I just mentioned a few of the techniques that can still be applied to verification, taken from the agile software world. I mean, we all know a lot of software techniques have been applied to verification, like, for example, mutation coverage, mutation faults, injecting faults in the design. Also, a lot of other things like exploratory, testing, which is really our constrained random testing, and a lot of other things. But we have functional coverage, and they don't have that. Anyway, so I was just talking about other techniques we could use. Something about analyzing the issues and the bottlenecks on your project, or having automatic notifications for bugs which take too long, and things like this. So with this, I'm coming to an end of my presentation, and I'll be more than happy to answer any question you may have. Thank you.
Okay, well, Kamel, thank you very much for that. There's a few questions already if you go to the chat window. You'll see, for instance, Spaz is asking, could you also apply this on the design side, or does the dependence on UVM prevent that?
Yeah, this was presented. This was implemented in UVM. So this was done as a, but this can be applied to anything, right? I mean, this is UVM code. So right now the implementation is UVM. Yeah, so this is applicable to UVM test benches. It's UVM code, right? But I mean, that could be applied to anything, right? I mean, that's that's implemented in UVM, but that could be applied to any kind of implementation, any view, any design. I mean,
Yeah,
the
I
idea
can imagine as long as the design's being released into your UVM environment, you can also handle workarounds inside the design, right?
yeah, exactly, and that's the whole half of it. You know, if you saw the presentation I mentioned, I always said, you know, you can handle workarounds in the test bench, but you can also handle workarounds in the design. And we have designers who do that. That's what they do, right? When they come in, they know the environment, they know the defect table. So they come in, they do a change, they do a bug fix, and boom, they just rerun the test. You know, they change a register, they change a constraint, they know what the defects are. So they go to the table, they can see their own defects, they can see the number, and they can see the action, and they can and they can do it themselves. That's the whole point. A big advantage of this is you don't have to be an expert, you know, in Systemverilog. You don't really have to know UVM. It's very simple. It's self-explanatory, right? We just sit down with them and we tell them, look, you know, there are 3 or 4 ways to do when you do your fix, and they can do it. And again, we've added the command line, you know, to be able to do it without even changing anything, but just giving them some notes, right? You can give them some notes, like for each defect, you just say, check that it's fixed, and you can just run it with these arguments too.
Okay, it does require a bit of discipline, though, I guess. No, not
No,
you know, you the infrastructure, but the telling the truth part about actually the workaround and
yeah, you have to understand the action, right?
Yeah,
You're right. What you can do as verification team, you can abstract this action and make simplified notes for each one, so they don't even know, you know, they don't even know what's happening behind the scenes, right? You could have another layer, right? And instead of changing constraints or, you know, changing a register, you can just say, you know, check that it's fixed, and then you have some code in between to do that. So you can always, that's always been a challenge for verification teams to kind of, you know, have designers use the test bench. So pretty simple ways, and you're right, that's a future enhancements too, which wasn't mentioned, which would be a good thing, which would be add some infrastructure in between so that the designer doesn't even have to touch or understand anything. I mean, he can just rerun, change the setting, and then he can look at the waveforms if he wants to.
Okay, next question. Alberto's asking, how many pending bugs do your team usually need to manage? I guess he envisages a huge table or something in this case. But is it scalable?
Yeah, you know, it is scalable. It's a table, and it's really a table. I mean, we have automation. We can, you know, we can query. We can see that in the log file. We can, you know, and that's what we do at the end, right? We sit down and we look at the table, and we're like, okay, oh, okay, we have some bugs, but these are not important. We can tape out, right? Or I mean, we look at this bug at this table frequently, almost daily, from the verification team. But it's a nice place where everything is there, and you know what's being applied. You know where the fixes. But yeah, it's going to be, and that's what you do when you tape out, right? You look at your bugs and you see, are they important? Can you tape out with these bugs, right? So that kind of helps you to interrogate live with the code. You can see that in the code itself. The beauty of it, it's all executable. It's all with you. It lives with your test bench, and you can also see the same thing for your test bench bugs too. Yeah. But I mean, maybe we have to think about scalability or presentation. You know, if that typically the number of bugs is pretty small. You know, and you can, yeah. But if it's big, then yeah, we would have to do some thinking about how to present that maybe in a better manner. I agree.
Thanks for that. Danielle is asking, have you considered sharing the solution? I guess the actual code base as open source Systemverilog package.
Yeah, that's possible. I think if anybody has some interest on the paper, you have my email, and yeah, I'd be happy to share it. I mean, the inventors of this are really CorrectDesigns, right? So, but they work for Teradyne with us, so we kind of implemented this, and we own this jointly. But I don't think it's a problem. I mean, if you can just talk to me if you have some interest in using the code. You can look at the paper. You see my email, kamel.belhous@teradyne.com, and I'll be happy to share the code with you. It's pretty simple. Any verification engineer can pick it up within a few hours. It's just, you know, it's a very smart concept. But the beauty of it, The infrastructure is pretty simple, very simple. You just have to adapt it to your own environment, right? You have a base class, you can create bugs, you can take some actions. These are the concepts. And then all what you need to do is just fill the details which are specific to the environment. Maybe in my environment, I call my tickets open, resolve, close. Maybe instead of resolved in your environment, you call them verified. Or, you just have to adapt a few enums. It's pretty simple. It's very easy to pick up. It's very, very, very sleek and very, very powerful. But like you said, you have a discipline. When you study the first time, this kind of, getting used to it, it's a change, right? And you don't need to copy all the bugs from your defect tracking system to your test bench. You don't need to copy all of them. I mean, there will be some you don't care about. There'll be some about documentation or things like that, which not an issue. Yeah. So yeah, please write me an email and I'll be more than happy to share.
Okay, we have one more question here on the chat. Aurelian is asking something that was in the back of my mind, actually. When a bug is actually fixed, do you remove the workaround code or do you just update the status of the bug?
I mean, it's disabled. It's a good point. It is disabled, but it is still there. Because sometimes, some of the bugs in the future may just bring this back up. We may have to revisit it and do the same or something different. So yeah, we don't, I mean, that would be a good thing maybe that we can do. It's probably a good suggestion. So maybe after we tape out the chip and everybody's happy, we could go and clean up the workaround. But to be honest, they don't really harm. They're there and they provide a trace. And sometimes, you may have some bugs related to the same thing, but which have a different signature or different failure. So this keeps a history, right? So this becomes more like a philosophical question. I'm not sure about the right answer. I have like two answers. I'm thinking about it because I didn't think about that. We didn't think about that. So I'm thinking one way would be, okay, you finish, you tape out, you're happy, everything is clean, and then you just go and you remove all these workarounds. That's fine. Or another method would be, no, I want to keep the history in case, a bug comes later from somebody in the field or whatever, and we want to see what's been done and what were the changes and what were the issues related to that piece of logic which was failing. So to be honest, I don't really have a yes or no question. That's something we need to think more about it. And that's a very smart question. Yeah, you can think about that.
Related to that, Aurelian's following on with actually the history question regarding the defect table itself. Does it contain all the defects that appeared during the lifetime of the project, or is it cleaned up?
No, it's really, it's a choice, right? You could say it's a choice for every team. Ideally, yes. Ideally, I mean, let's say, for example, right? Let's say you have a bug. You have a bug, and the designer is next to you. You call him, you look at the waveform, he does the fix. Then there's no point putting in the table, right? So I don't think it's every single bug, right? It's every bug that needs to be tracked and resolved, and that we need to know about. Because a lot of the time we do fixes, we do some hacks in our regression, some changes, or so this is to enable you to have a cleaner regression really and make progress. So it's really, yeah, normally in theory, any outstanding bug, right, can hurt you. So you want to take care, make sure you don't forget about it, make sure you fix it. But if you have some bugs that, somebody somewhere, you're working tomorrow, you come back the following day and somebody find the bug and it will solve, you don't need to put it in this is not supposed to be an inventory to show all the bugs. No, that's what your original defect tool tracking system is doing. This is
sorry, Kamel, I think the question's more along the lines of if you did have a workaround in your code base that had a corresponding entry in the table, and the bug gets fixed, do both the code and the table, I guess if you're going to leave the workaround in the code, I might also expect the defect to remain in the table but be shown to be closed. Somehow.
Yeah, it will not be removed. No, it will not be removed before tape out. Yeah.
Right. Not necessarily all bugs will go in there, but the ones that did go in there will stay until tape out is
yes.
Would have to be like that, but that's your recommendation, yeah?
Yes, yes, yeah. We want to keep track because, you know, when you fix a bug around some area of logic, it doesn't mean you're not going to have other bugs related to that specific logic too, right? So you really want to keep the history. After tape out, it's a different story. Then you can do whatever you think. It's okay. You know, it depends. You know, if you finish a check, it depends. Yeah.
Mm-hmm. Okay, well, we're finished. We're out of time. I'd like to thank you, Kamel, on behalf of all the listeners. Unfortunately, you don't get a round of applause, but you know it's there anyway in the ether somewhere.
Yeah, I can feel it. So thanks. I mean, these are really good questions. I really appreciate your time. It was really good question. I appreciate you attending. Thank you so much, and thanks, Mark, for hosting us.
Okay. Well, thank you very much,
Kamel,
and for all the listeners as well.
Yeah. Take care, everybody. Have a nice day. Enjoy the conference. Bye.
Bye. Bye, everyone.
Thank you.
على غبي قفلها السيشن هو. Hi, Mr. Mark. Can you hear me? It's our time to close the session. Thank you, everyone. I'm gonna close the session now.